like giving this talk because when everyone thinks of gold in the United States, they think directly of California and the placer mining and the 49ers and how much gold came out of California, blah, blah, blah. And beautiful gold came out of California. This is from the Allegheny district at the north end of the Mother Lode. And you can see that beautiful leafy gold. Unfortunately, very little of this is mined in Nevada. What's mined in Nevada are nanoparticles of gold in limestone hosted deposits known as Carlin type deposits. This is, to be honest with you, I forgot the technique. It's a scanning transmission electron microscopy technique. And it's showing one of the large gold particles that you'll see in a Carlin type deposit at 2 nanometers. And all that kind of web texture is interpreted as a ray of gold atoms. So basically, as the settlers rushed across the western US to get to California, they missed all of this Carlin gold because there's absolutely no way you can pan something like this. So this is the idyllic view. There you go, going to sluice box in California, panning in a pan there, old time, guy panning for gold in a river in Northern California. We just don't see that in Nevada. There's no rivers. There's hardly any placer operations in Nevada. Nevada's modern day gold rush. Well, this is an example. This is one of the world's largest gold mines, the post-Betsy open pit gold mine on the Carlin Trend, located just northwest of Elko, Nevada. At the time of this photo was 37 million ounces. This deposit has over 60 million ounces now in past production and reserves. It's almost, what is it, 2,000, no, it's about 3,000 feet long and about 1,000 feet deep, the open pit. And it's all bulk mining. So you can see a big haul truck there. You're basically mining a lot of relatively, low grade. This material here in this pit was typically about 5 to 6 grams per ton gold. And what they do is part of it, when they first started mining in the Carlin Trend, they were only mining shallow pits in which the ore was all oxidized. So it's very important whether the ore is oxidized or not, because if it's oxidized, you can just run it through a mill with cyanide and extract almost all of the gold, or put it on a heap leach if it's lower grade and leach almost all the gold. But if you can see that in this slide here, all the oxide is near the top as you would expect it, because that's where most of the rainwater would be and weathering it. Then you see this dark material in here. This ore has not been weathered and it's sulfide bearing. And the problem is you cannot leach the gold out of the sulfides very easily. And it requires much more expensive techniques and investment. And in this case, in the Carlin Trend, it's an autoclave. And it's basically oxidizing the rock in real time at super high temperatures under oxidized conditions. And an autoclave will be like close to $1 billion. So obviously companies like oxide ore better than sulfide, but some of the sulfide ore can be extremely high grade. For Nevada's,
John, I'm going to interrupt for a minute.
Sure.
Is there a way, there's been a request, could you make your slide take the full screen?
Let me see how I can do that.
I think you need to.
Slide control maybe? No.
I think it's under display settings.
Display settings. Where's that? Here?
Upper left.
Upper left. Oh, display. There it is. Duplicate slide show.
No, above that one. Yep, you got it.
Oh, there we go. Great. That is much better.
Thank you.
Move this off. There we go. Okay, so this shows you a nice map of all the different Carlin type deposits, not in the whole state, but just in that little box there in northeastern Nevada. And there are two main trends. The Carlin trend, which was the first place where gold was, Carlin type deposits were discovered. There's the little town of Carlin here. Elko would be off the slide off to the east here. And you can just see this numerous deposits, they cluster. So it's not just a one mine. It can be there's several open pits in here and several underground mines as well. And so this goes down towards into the Pinion Range, and there's much smaller deposits down in here. The other major trend is the Battle Mountain Eureka trend. And it starts with the Getchell mine, which was one of the first Carlin type deposits discovered in the 1930s. They didn't know, that it was a Carlin type deposit when they discovered it. But there's some very large deposits up in here. And then you go down into the Battle Mountain area and you don't get Carlin type deposits right in the Battle Mountain area. There's copper deposits with gold. But then you start picking up the Carlin type deposits down here in the southern part of this trend in the Roberts Mountains and into the little town of Eureka. So there's two major trends, and then there's a third one. Well, part of this trend, this is a little bit dated, is the Cortez area in here. The Cortez area was discovered by the USGS in 1965 by sampling. Amazing, the USGS did that. And it's wound up going to be challenging just about the same amount of gold that was mined in the Carlin trend. So these are the two big districts. About 80% of Nevada's gold is in these Carlin type deposits. About 151 million ounces of gold have been mined from Carlin type deposits, and there's 100 million ounces of remaining reserves. All in all, in this area in here, there's over 275 million ounces of gold in this 200 by 300 kilometer area of northeastern Nevada. Just for kicks and giggles, I compared it to South Africa and the Witwatersrand, which is the biggest gold field in the world. Both these maps are at the same scale. This is the same image I was showing you in the last slide. And this is the Witwatersrand in South Africa. Basically, Carlin trend, this map area is probably the second largest concentration of gold on Earth after Witwatersrand in South Africa. Gold production. Let's see, this is gold production from 1835 to 2014. Both in the overall production in the United States. And then in orange is production from only Nevada. So you can see the 49ers, 29 million ounces, mainly from placer mining from 1849, 1859. Then they went to lode mining, hard rock mining, and their production kind of decreased off. And then in the West, this is just very generic, but includes mines like Cripple Creek, Homestake, big underground gold mines that contribute a significant amount of gold. And then in here, yeah, I'm trying to remember, I forgot exactly who was producing at this point in here. Oh, what this is just saying is just, there was a, gold was very, only about $20 an ounce. And then up in here, they increased the price to over 30, and then you got a big increase. And then see this precipitous drop. That was because during World War II, gold mining was considered not important to the war effort. So all the gold mines were closed, except for the Getchell gold mine in Nevada. And then you see at the end of World War II, we get an increase in mining again, gold mining, and then it just steadily decreased up until this point here, but you see this little blip here, that's the discovery of the first deposit, Carlin type deposit on the Carlin Trend, named the Carlin deposit. And so you see that blip, and then all of this is production from the Carlin Trend, from that Getchell mine area, from the Cortez area, and this is the current boom, 261 million ounces of production underneath this big blip in here. In comparison, on the bottom is California, starting from 1850 to 2010. Again, here's the big placer mining, dropping off, and then really bottoming in 1890. Kind of went at its own up and down, but not a big, great increase. Again, until the 1930s, where there was an increase in the price, and then the drop in World War II. And then basically the underground mining was basically finished in California by 1960. This is because of the increase in interest of gold in the 70s. There were some small open pit mines in California that brought in a little bit of production. So just from roughly the same age range, Nevada's produced 210 million ounces in this 170 years. And then in this 160 years, California has only produced 118 million ounces. So California, well, I would do just outlining California's gold, a brief history. I'll talk about it briefly, and how California's gold deposits form. And then I'll talk about Nevada's early silver gold history in epithermal deposits, namely the Comstock Lode, Goldfield, and Tonopah being the most important. And then I'll jump a little bit in more detail into Nevada's Carlin type deposits, what they are and how they form. Modern gold and exploration in Nevada, and how Nevada Bureau of Mine and Geology helps maintain Nevada's ongoing gold rush. We just saw this slide here. Again, most of the 118 million ounces, 60% of it was placer, 40% of it was lode. When you look at this, you can see some of the bigger events that I spoke to in a couple of slides ago. This is the California gold rush, mostly placer mining. Then there was kind of a drop here, and then sort of an increase, and doesn't really show it as a big increase, but they made a lot of money or mined gold profitably by hydraulic mining. However, hydraulic mining made a mess of Northern California, especially agriculture in the Great Valley. And so it was banned in the mid 1880s, and that affected the production significantly. And therefore, there was really no significant placer mining since 1880 or 1890. This was mainly underground lode mining. For example, in Grass Valley, California is the Empire Mine. And I already mentioned the 16-to-1 underground mine in the Allegheny district at the north end. And then here, finally, they allowed the gold price to float in 1970. And that's where we see the increases, both in Nevada and California, just because the price of gold increased significantly in the 1970s. So placer gold, yeah, nothing fancy. This is the early, probably 1860 photo. But this is the damage that hydraulic mining does. This is in the Malakoff diggings, 1890, near this little town of Nevada City in northern California. They basically took water from the high Sierras and just based on its hydraulic head, shot it through cannons and washed away old Eocene stream gravels that had placer gold in them, and was very efficient in getting that gold out of those old Eocene river gravels. So again, there was a long period after placer gold mining kind of came to an end around 1900. There was a lot more underground mining. And this is the shaft at the Empire Mine at Grass Valley. You can see all the miners going down and chasing fairly thick quartz veins with significant amount of gold. Just to give you a kind of a brief background of what happened in California in 180 million years ago. This is a paleogeographic representation. There were fringing island arcs off the western coast of the United States. Eventually, with time, these island arcs would get closer and closer to the coast and basically smash onto the continent and form a lot of deformation in the form of thrust faulting and folding and a lot of metamorphism. In the late Jurassic, there was, there's still some of this, a lot less magmatism. By the time you get to the late Jurassic, and left lateral faults forming in this area, not necessarily the ancestral San Andreas fault, but once these terrains get accreted to the continent, they tend to move in a strike slip type of motion. And in the early Cretaceous, 125, this is when a lot of island arcs started colliding into Western North America. And this was the beginning of arc magmatism, a subduction zone underneath that started forming the Sierra Nevada batholith. And at this point, at this time, at 125, is when most of the gold in the mother lode actually formed. The other thing, and this goes to a lot of big gold camps. Big giant gold camps don't form this randomly. It actually, there's like big events, plate tectonic events that happen that result in the formation of these big camps. So for example, at 120, I think this, I can't see this here, but I think it's about 140 million years ago, the Farallon plate was forming in this direction. But at 122, all of a sudden it switched direction and now it's going this way. And that corresponds, and that occurred at 122, and that occurs to where most of the gold, when you date the gold mineralization in the mother lode, it's about 122. So these big changes in the tectonic plates can result in a lot of action, let's say, metamorphism, faulting, whatever, that actually leads to the formation of bigger deposits. So here's a cartoon of one of these subducting plates as these terrains, these island arcs get smashed against the continent and form all of these reverse faults. And then the plate is going underneath it. We're getting granites forming the proto Sierra Nevadas. And a lot of things happen when you're subducting these oceanic sediments deeper and deeper. You go to different degrees of metamorphism. And I'm going to jump to, I'll stay here. And what happens is, as you're pumping these sediments down in here, they might go to very low metamorphism, pumpelliate, green schist, medium, 350 degrees, 400. But then when you go into amphibolite, you drive it down to close to 500 degrees C. And as you're going to higher and higher grades metamorphisms, you're releasing more and more fluid. Okay, so each of these metamorphic reactions are dehydration reactions. And when you see in these mother lode deposits, these vein deposits, you see a zonation in the trace elements. Gold commonly hangs out with arsenic in these deposits, relatively deep. And as you get shallower, you start picking up tellurium, then you start picking up antimony, and then you start picking up mercury and antimony. And this is not just in California. This is also seen in British Columbia, and Eastern Canada, and elsewhere in the world. So you can see the depths, at least in this epizonal area, you're looking at depths of 1 to 5 kilometers they're forming. Mesozonal down in here, 5 to 10. And there's been really nothing mined this deep, very little at 10 to 20 kilometers. This is the estimated depth at the time the deposit formed. Here's some of the terrains. Here's the Sierra Nevada again, formed by a subduction zone. And then we're getting into the northern Sierra terrain, again smashed up against the Sierra Nevada. And the Calaveras complex is another accreted terrain. And this is arc magmatism of Jurassic and Triassic age, so older. And then a middle to late Jurassic sequence out here. So again, these are just terrains smashing in and diving down and being metamorphosed. Yeah, so the arc terrain accretion, mainly between 272 and 166 million years ago. A lot of thrust faults and suture zones as these terrains smash up against the continent between 197 and 177. And then between 160 and 125, a lot of sinistral strike slip motion coming like this. So Malonis fault zone is one of them. That is the main fault zone along the mother lode, is the Malonis fault. That's where most of the gold deposits of the mother lode formed. And then you're looking at post 125. Well, right at 125 is, like it says, most of the gold deposition. Then after 125, it switches to dextral, which is right lateral faults. And then at 125 all the way to 80, it's just development of more and more of the Sierra Nevada batholith to what we see as it looks today. Okay, so back to Nevada. At this point, there was no really no production in Nevada prior to 1860s. So what happened was a lot of the ground, you know, the easy placer mining on the mother lode was running out. The shallow underground mines were being mined out. Finally, some prospectors got sick of it and took a chance, head over to Sierra Nevada, and heard some words that there might be some potential south of Reno. And what happened was they went into what is stream, I forgot the name of the stream. It's just east, just west of, just east of Carson City. And they were just kind of panning. Oh, they get a little bit of color of gold, but then they got a lot of black shiny stuff. And they didn't know at first what it was. They went back to Nevada City and found out it was silver. And so this was the discovery of the Comstock lode, the first part of it. And this happened to be one of the world's greatest, biggest, highest grade epithermal deposits that was ever mined. Its heyday at Comstock was from 1860 to 1885. It was mainly a silver mine. About 180 million ounces of silver were mined from the Comstock lode in the 1800s, and about 20 million ounces of gold. So after the Comstock petered out, and also around 1905, when cars were invented, prospectors got to be able to travel Nevada a little bit more easily. And that in that period, 1905, led to the discovery of Tonopah and Goldfield. Tonopah was also a silver district like the Comstock. It produced 180 million ounces of silver and about 8 million ounces of gold. Goldfield was almost entirely a gold mine, 5 million ounces, but importantly, the ore, all that 5 million ounces, the average grade was 1 ounce per ton. So it was a very high grade deposit, very profitable. Goldfield was one of the most nicest cities or towns in Nevada at that point, near the turn of the century. Again, here is just the increase of the price, and here's the discovery of the Carlin type deposit. And the boom, again, is the discovery and production of Carlin type deposits. Okay, so Nevada This is the Savage Mine, Comstock, one of the first mines that was built in the 1860s. This is the Mohawk Mine, the most productive mine at Goldfield, 1908. See the old timers. A lot of the Goldfield mine was in breccias, and you can see all this native gold rimming the breccia fragments. So this was an incredibly high-grade mine. And then this is a very strange mineral. It's very rare, but it was found in the Comstock, but by no means was it the main gold mineral. Uten bogenardite, but anyways. So think of epithermal deposits like geothermal systems like Yellowstone. And more from the exploration side, from mineral exploration companies become, it's part of this wave of transition of just chasing gold assays to becoming more conceptual in exploration models. And epithermal deposits form relatively shallow, within a kilometer of the surface typically, but they have many features that active geothermal systems have. So there can be silica sinters, which means there was a lot of upwelling of hydrothermal fluids that were silica rich and it vented at the surface. So you're really close. And how these epithermal deposits form is as that hydrothermal fluid is coming up to the surface, it begins to boil. And when it begins to boil, that is the mechanism that deposits the gold in the veins. And so just like a geothermal system, these epithermal deposits, think of them as paleogeothermal systems that would have these same type of fluid flow features. So here's gold deposition by boiling. Gold in hydrothermal fluids, both in Carlin type deposits or epithermal deposits, is almost entirely transported as this gold bisulfide complex. So there's two of these HSs, so that's why it's called bisulfide. And then with a little hydrogen and a little reduction by boiling, you deposit gold and you're losing H2S. So as you're boiling, that H2S rather would like to go into the vapor phase, not remain in the liquid. So when you lose this, the gold becomes free and deposits. And so it can happen over and over these boiling events. So for example, the fracture might break open and then it seals up and then it breaks open and then it seals up. And then you can see that in all these bands of gold are different sealing up and breaking and depositing gold by boiling. This is another example. I actually was fortunate to go here. It's a crazy place, but it's Papua New Guinea. Same thing, a lot of gold veins in which there was a lot of native gold in veins and fault zones. Okay, back to the discovery of the Carlin trend. This was very interesting. Again, it was missed by all of the settlers that came across or all the other prospectors that came across Nevada because they couldn't pan it. And Carlin type gold in Nevada was first discovered in the limestone and gold acres in the Cortez area, which I mentioned in the 1920s, and in the Getchell area in the 1930s, but it was underappreciated. Basically, you couldn't pan it, you couldn't see it. The only way that you could tell there was gold is by assaying it. The important thing by the 1920s and 1930s, assay labs were becoming fairly common. Now, what happened was a fellow at USGS, Ralph Roberts, who helped discover the Roberts Mountains thrust in Nevada, suggested gold should be found in windows through the thrust in the lower plate. In a talk, he presented this talk at a Geological Society of Nevada meeting in Ely in 1961, in which this guy, John Livermore, attended. And what happened, Livermore was a Newmont employee, Newmont Mining, and John Livermore and Alan Coop then took his advice, talked to him after the talk, and basically Ralph Roberts said, well, I've seen a lot of these windows in the Carlin area. So Livermore and Cooper went up to that area and found the Carlin deposit in 1961. At that point, it had 3.5 million ounces before it was mined. And they had a trench that had 80 feet of 0.22 ounces per ton. That's pretty good. And so that mine was the first. I mean, Getchell and Gold Acres were put into production, but this was Carlin mine for that time period was a significant producer. What happened was, so we started, okay, Carlin produced in 1965, made a lot of money. All the ore was oxide, low price to produce. And then the 1970s came, and that was the start of the big gold rush, where there was floating of the gold price. It was not set at, it was not set to a specific price anymore. So, and there was also now affordable gold assays at low detection limits, getting down to about, 100 ppm. Excuse me, about 50 ppb in some places. What happened was the main exploration technique was looking for jasperoids, because the Carlin mine had a jasperoid with some gold in it. So if you don't know what jasperoid is, it's a replacement of limestone by silica, massive silica. And this is a common hydrothermal alteration that occurs when you have a lot of carbonates. The other thing that was happening at this time, drilling became much more inexpensive. So this brought a lot more companies, a lot more drilling, and a lot more exploration. And then the other thing that was discovered in the 1970s, I mentioned before, was the process of heap leaching. That basically, when it first started, was just piling up rock on the ground and spraying cyanide on it. Of course, you can't do that anymore because of environmental issues. But it was a very cheap and efficient way of mining very low-grade oxidized gold ore. Okay, so Carlin-type deposits, they're hydrothermal, they're epigenetic, meaning they're forming after the rocks have formed. Disseminated replacement bodies. They have few, if any, veins. They're adjacent to high-angle faults and are amenable to bulk mining techniques. So when they first started being mined, it was mostly open pits. But as the open pits got mined away, and the pits got deeper and got into the sulfide ore, the companies didn't know quite what to do. But there was a company, I'm trying to think, can't think of its name. It was kind of a smaller company, and it took a chance, and no one ever did this before, in around the late 1970s, and drilled a 2,000-foot hole near the Carlin-type deposit. And no one had ever did that before. And they got a thick section of sulfide ore. And of course, they said, well, we can't, you can't get the gold out of the sulfide ore, but they were able to get it out of the gold ore. And eventually what happened was Barrick Gold took over that company and basically developed the Northern Carlin Trend, which again is this big, huge post-Betsy open pit. And then Barrick also explored underground and found even higher grade stuff underground, such as the Meikle mine that averaged about 7 or 8 grams per ton. So Carlin-type deposits are almost entirely hosted in carbonate rocks. Those carbonate rocks can be silty, quartz silt. The alteration shows are variably leached and replaced by silica, and they contain arsenian pyrite and late arsenic sulfides. So this is from the Twin Creeks mine in the Getchell area. And all this is the mineral orpiment. And sometimes they close parts of the Twin Creeks mine to let mineral collectors come in and pay a premium on nice orpiment samples. But this is the occurrence of gold. This is a scanning electron microscope image. Scale here is 20 microns. And in these images, the brightness is a function of the average atomic weight of the elements in these minerals. And so this dark area is pyrite, FeS2. And you can see it has these bright rims around it. Those bright rims are arsenian pyrite. So this pyrite contains, for example, up to 20, 30 weight % arsenic. And then it gets a little bit darker again. And so this one still is arsenian pyrite, but has less arsenic than the bright rim. Back to here is our gold nanoparticle I showed earlier. And you can only, and the other thing that's causing the brightness here is not just arsenic. What's really causing the brightness here, I misspoke earlier, what's really causing the really white, bright rim here is gold. So the gold contents can be, upwards of about 20 ppm in the arsenic. And this is probably out here, probably more like 10 ppm or 5 ppm. And so again, the gold occurs mainly, not even as a mineral, it's as an ion. And this was only found recently in the last 5 years, maybe 5 to 10 years, that the gold is not as native gold for the most part, it's as ionic gold, Au+1. And the idea here is, why do you have Au+1? Is that pyrite has a strong negative charge to its surface. And so negative charges will attract positive charges. So the idea is that that could have been a very efficient mechanism for gold deposition, was when that the fluid interacted with this negative surface, it sucked the gold ions out of the gold sulfide complex. In weathered ores, gold occurs as native gold grains, but they're mainly less than 5 microns in size. And so that's why they put it on a heap leach or run it through the oxide mill. It wouldn't make any sense to run it through a sulfide ore, that's for sure. What do the rocks look like? Well, there's these thin-bedded carbonate rocks. So over to the left here is unmineralized limestone. You can see some deformation folding like this. And then this on this side is a high-grade gold ore replaced limestone. So this is altered, hydrothermally altered. So what we do in our thin sections to get at porosity is we put epoxy on our thin sections, blue epoxy. And so the blue epoxy is showing the where there's pore space in these rocks. So in this unmineralized limestone, you can't see any blue. So there's very little porosity and permeability in this limestone. But after it's been altered by the hydrothermal fluid, it's very blue. There is a lot of porosity developed in this rock. And when you put in a secondary electron microscope image, this is what you see. You don't see any more carbonate. You see pyrites that are bright, like I showed before, and then all this nice quartz, doubly terminated crystals, clay, kaolinite. And that's basically what happens now, because that rock is so porous. Once you start dissolving the carbonate, you can put more and more ore fluid into that limestone unit until you run out of acid. And so the process here is starting with a silty carbonate. Here's the quartz silt grains. Here's maybe a nice rhombohedral dolomite. Here's maybe some orthogenic case bar. And then here's the calcite making up most of the limestone. You hit it with acid, hydronium. Calcite likes to dissolves much more easily than dolomite. Dolomite just rounds off, and that's called sanding. So, the dolomite's almost like a sand grain. Nothing happens to the quartz because yes, it does nothing to the quartz, but your K-spar goes to illites. And then to drive the mineralization is what you hope for is that the calcite or dolomite has iron, because once the calcite and dolomite begins to dissolve, it releases the iron. The iron reacts with this, the HS, to form pyrite and breaks down this complex, and therefore the gold is free, and then it gets incorporated into the pyrite. So the gold, arsenic gold pyrite preferentially nucleates on pre-existing pyrite grains. So these are like diagenetic pyrite, but the gold likes to nucleate on those existing grains. There's a little bit of minor cooling, hydrothermal quartz forms, and you get a rock that looks like this, where this is the gold-bearing pyrite. Here's the silicification. And let's keep going. So this is a cross-section of the original Carlin mine. And here's the alteration. Here's a jasperoid body. And so this would have caught their interest because it would have cropped out over the ground on the surface. Next is a silicious argillic zone, which probably only would have cropped out, moderately. And it goes down and follows the stratigraphy like this. So this is the Roberts Mountains formation in here, and this is the Popovich formation in here, and it's kind of following, the ore zone is following the contact. So once you just start dissolving carbonates, you can put more and more and more of that fluid. So it's kind of a positive feedback loop. Here's the Roberts Mountains thrust. So these are all carbonates. And then this is the upper plate, which is a silicious rock, typically cherts, greenstones, and some siltstones. Whereas all these are all carbonates down in here, and that's what hosts almost over 90% of the Carlin ore are carbonates. Let's see. Most of the Carlin type deposits formed in the Eocene, which is between 42 and about 34 million years ago, or about 34 million years ago. And at this time in Nevada, there was a lot of still subduction zone occurring, but by the time it's the Eocene, the slab is very flat. Okay, so the slab is flat, and therefore there's no magnetism occurring in eastern Nevada because the slab is just simply too fat to drive off fluids, and there's no room for the asthenosphere to get in there, so magnetism shut off. So what happened though is when you have an oceanic slab on the bottom of lithospheric mantle, that slab is cold, and because of that, it's unstable and it will peel back with time. And that's what happened in the early Eocene to middle Eocene, is the slab rolled back starting in Idaho and started rolling back to the southwest. So there was no magnetism, but finally by 40 million years, it got into northeastern Nevada. And then by 36, it's down in the Cortez area. And then by 25, it's already almost near the California border. So it was kind of a marching of magnetism going in this direction to the southwest. So if, the mineralization follows closely time and space, that sweep of magnetism, the formation of the Carlin type deposits. I don't want to, probably running out of time here, but I don't want to get into the controversy over the source of gold. All I can tell you that there is debate whether it comes from sedimentary rocks, whether it comes from magmas, whether it comes from metamorphic rocks. Bottom line, it doesn't matter. In Nevada, there's just enough sources for gold. You don't have to worry about that in your exploration. Interestingly, we talked about what happened for the mother lode, a change of plate motions. Here's the Hawaiian Islands, and this is the Midway area. And you can see the change, the abrupt change in the Hawaiian Island chain And that was due to a change in plate tectonic motions right in the Eocene, which is the time when the Carlin-type deposits were forming. So another example of a big tectonic motion affecting a formation of a giant district. This just shows various types of models of ore deposits that form in Nevada. There's gold skarns when you put in an intrusion and you interact it with limestone, you form skarn. And they can be copper bearing, they can be gold bearing. There's very few, if any, massive sulfides in Nevada. And then these are the epithermal deposits that form up near the surface. Carlin-type deposits are thought to be distal to these intrusions. We're getting more and more data that that might be the case, that they are probably related to the intrusions. And just showing examples of field work when I was a lot younger and doing helicopter work out in Nevada. This is an extremely fun profession, I'll tell you. I couldn't think of a better profession. I mean, I'm from Indiana, and to be honest with you, I read all about the gold rush. I didn't think no one was ever looking for gold again. And then I saw a show on PBS on modern gold exploration, and that's when I decided that's what I wanted to be. 3D modeling is becoming more and more important. For example, this was at the Getchell mine, the Turquoise Ridge Underground mine. We modeled the Getchell Fault. This was the top of a sedimentary debris flow breccia, the bottom of the debris flow breccia. Purposely, we did not model the gold, but then we modeled the gold and all of it fits right in that debris flow breccia. So the 3D modeling is very powerful to understand the controls on gold. Yeah, so there right now in Nevada is probably as much, if not more activity than I've ever seen in mineral exploration, still for gold. I mean, there is stuff going on for lithium in Nevada and other things. Silver's seeing a lot of exploration. And like I said, I'm a director of this Center for Research in Economic Geology. It's just a program that's funded by companies, by donations, which the companies like because they don't have to pay overhead like a grant to the university. And what happens, we bring students in, we have them start in the summer where they work on a project with a company, and then they start their true degree, graduate degree, most of our masters in the fall. And so they get a lot of experience in the summer, and then when they get to school, they start their research running. And it's been very successful. All our students get jobs, and I hate to say it, they get paid just as much as I do. They're doing a very good job once they graduate. I think I'm finished talking for a while. If there's any questions, feel free to ask. Chat room.
Yes, John, we have one question so far, and this is from Diane Lynch. Carlin deposits, what do the windows look like that those three guys were looking for?
Right, so the windows, what you'll see is there'll be large